Thanks for coming, everyone. This webinar is a reprisal of a workshop that I gave in person at a climate risk event at New York Climate Week. And I made a fun little notebook there showing how you can replicate some of the results from official New York climate risk predictions using Arraylake, using Icechunk, using open data, using open source software. And I thought it was pretty fun. And so I wanted to show you all rather than keeping it just for the people who attended that event in person. So let me find there you go. So just a brief intro before we get into the notebook. Um, so for those of you who don't know me, my name is Tom. I have a background in multiple different fields of science, but I pivoted into geoscience because I was interested in questions of climate change, climate risk. And I did that pivot by being a maintainer of various open source libraries, including X-ray and in the XAR ecosystem as well. So I pivoted from plasma physics to oceanography, which are surprisingly similar. And I work on, X-ray projects, our project, and the Pangeo community in general. And I now work at Earthmover, where our mission statement is to empower people to use scientific data to solve humanity's greatest challenges, which I think that predicting climate risk is pretty relevant to this. Earthmover is a public benefit corporation. Um, and our team has a lot of scientists, a lot of open source software developers, including Ryan and Joe, who I met both through the X-Ray project, and other engineers with different backgrounds of building scientific data infrastructure at some other companies previously. Um, so the motivating question for this notebook was essentially just the question of how easy is it now with modern data tooling to replicate official climate risk projections? Um, and I'm going to argue that it's actually really quite straightforward now, like surprisingly straightforward, using the power of like the cloud, open data, Arraylake. So let me show you that. So the notebook that I'm going to use is available publicly, public GitHub repo. This link, which I think we'll drop in the chat.
I've dropped it in. I couldn't find a chat, so I've dropped it in the Q&A if anybody
Great.
can see it.
Thank you. Um, you can always just go to the Earthmover GitHub organization and find this repo anyway. This repo basically just contains a notebook in Marimo form rather than a Jupyter notebook. There's also a Jupyter copy of it as well. I'm going to talk about Marimo a little bit. But the combination of using Marimo and also this other tool, UV, means that if you want to run this notebook as well, it becomes extremely simple. As long as you have UV installed, which if you're a Python user of any kind, you probably do at this point, because it's rapidly becoming like the go-to package manager, then you just need to run this one line, and it'll start up the notebook on your machine. So if I change what I'm sharing again, let me just. So because I've already cloned this notebook locally. So I've cloned the repo locally, and all I need to do to run it is UVX, Marimo, edit, sandbox, and the name of the notebook. So um, UVX is just like UV's one-line command for running particular other tools such as Rough, or in this case, Marimo. Sandbox tells it to install inline package dependencies. So the notebook dependencies are declared within the notebook itself, which is pretty cool. And then edit will allow me to edit it. So if I do this, it creates a sandbox and kickstarts the notebook, and we're already here. And what's neat is that we already have the correct dependencies, and there's a lot of them. So this first cell takes a little while to execute and download all of the various things that are required, but it will then just immediately work, which is a really neat way for running webinars like this. Then that combination of UV and Marimo is really powerful because if you've ever run like a participatory workshop before, then you'll know that it's like a lot of the challenge is just like getting people setting up to be even running things in the first place. Um, the next thing we need to do is, so once we've imported all of the various dependencies that we're going to use, um, we, in order to calculate some climate risk indicators, we're going to need some climate data. To get at the climate data, we're going to use Arraylake as our data catalog. So the first thing to do is we log into the web app, which we can do by clicking on the web app itself. Um, and then you can see the data set that we're going to use. Or you can do it programmatically using Python or from the command line. So the particular data set we're going to use is a subset of ERA5 here stored in Arraylake. And yeah, so we can view the repo in the web app. And in the Arraylake web app, we can see a description of what's in the repository. So surface variables from ECMWF's ERA5. But we can also see that we have various groups. So we're effectively seeing the ZAR store layout of the data. So we can see there are various groups. We can see inside those groups, we have various variables. We can see the shape of the variables, the data types. We can click through and see attributes and so on. We can see different branches of this repository. We can see the history of commits to the repository, and who committed them. So it's very much a GitHub-like experience. For the purposes of this notebook, this is just our source. So initially, we can view all sorts of information about this data source. So for example, if we do client get repo object, which tells us metadata about the Arraylake repo, we can see that whoever created the repo wrote about where it came from, what type of data is in it, which is Icechunk. But to actually get at the data, we need to get the underlying Icechunk repo. You can see this happens very quickly because we've not actually downloaded any data yet. We've just downloaded the ZAR metadata effectively. And so Icechunk enables a lot of what we're going to do next. Icechunk is Earthmover's open source transactional storage engine. You can think of it as version controlled multiplayer ZAR, or alternatively, you can think of it as Git for ZAR. It's extremely cool and powerful, but mostly for this notebook, it'll be behind the scenes because Icechunk presents a ZAR-like interface that X-Ray will read from. And although it's really Icechunk that's doing all the fetching of the data, then once we start our read-only session, read-only because we don't need to modify the data for this notebook, and once we get the ZAR store interface, we're not going to need to worry about the fact that this is Icechunk again. So in the same way that you might be used to doing X-ray open dataset on a ZAR store or X-ray open ZAR, we can do the same thing on the Icechunk store. We're going to specifically open this group, the spatial, which in here means the spatially chunked data within this particular store. We'll come back to the relevance of that later. And we quickly get to see our standard X-ray dataset telling us all sorts of information about what's in the store. This is the same kind of information that you can see in the web app, but it's a lazy view of all the data. So you can see the overall dimensions. It's a big sort of three-dimensional cube of surface variables here. But what's neat about this is there's 40 terabytes of data in there. And it could be even larger than that. So we obviously did not download 40 terabytes of data. We only downloaded the ZAR metadata. And the reason that that can be done in, how long did that take? 2.5 seconds, is because ZAR is a cloud optimized format. meaning that the metadata is separated from the actual data. This link goes to a blog post I wrote all about what it means for something to be a cloud optimized data format. So I already think that's pretty neat. Like the fact that this is even possible is really like one of the main arguments for cloud native analysis ready cloud optimized data, which is like kind of a buzzword in our field now, but it was basically a term that I think Ryan just came up with. Um, and the cloud optimized is what allows us to access it so quickly, and analysis ready means that it already has all of this metadata that we need in order to understand like what the names of the different data variables are and things like that. So the first thing we're going to do is just have a look at some of the data. There's lots of interesting variables in ERA5, but let's try just plotting one. Precipitation, interesting. Let's just double check that CP is actually the one that we want. By here, we're just getting the particular attribute metadata of the CP variable. We can see that it says its long name is convective precipitation. So, okay, that sounds like a variable we'd be interested to plot. This whole data set is global. Which means that if we want to plot it on a 2D screen, we have to decide how we're going to handle the map projection somehow. So let's use the open source Cartopy library to use an orthographic map projection centered over New York City for New York Climate Week. And we're also going to select a specific time because we have global data hourly going back to 1975 in this data set. So here we can see what, according to the ERA5 reanalysis, the precipitation was over this entire hemisphere centered on New York at this particular point in time. And it's taken us just a few seconds to get that. There's an interesting feature in this plot, which weather aficionados might recognize. If you look at this date, then something interesting happened later that week, which was that Hurricane Helene hit the southeastern US. And you can actually basically see the weather pattern that becomes Hurricane Helene is here, like just on the western tip of Cuba, which is pretty interesting. And it's pretty relevant for estimating climate risk projections because Hurricane Helene went on to cause $80 billion in damage. Let's try something else. Let's try a different type of analysis. So we've shown how easy it is to just get at and look at some of the data. Let's try calculating some quantities that are related to climate risk. So one interesting quantity, a derived quantity that we might want to calculate is called the wet bulb temperature. And the wet bulb temperature is a measure of heat stress on humans and how it affects human health and safety. And the short summary of wet bulb temperature is that prolonged periods above a wet bulb temperature are likely to be fatal to even fit and healthy people because it basically means that you physically struggle to sweat enough to keep cool. So wet bulb temperature is a function of actual temperature, but also of humidity, because humidity makes heat waves feel much worse. So let's try calculating how high the wet bulb temperature got during the 2024 Indian heat wave, for example. So to do that, we'll first subset the data into a bounding box over India. So we're just slicing it down to a square in longitude and latitude. We're going to keep only the variables we need to calculate the wet bulb temperature. And then we're going to load just this subset of data for a particular time period within the height of the 2024 heat wave. So again, we've quickly got that data and we've downsampled to a particular, we've subset it to a particular time point. And we've only got the data variables that we need now. So we've got the surface pressure, the temperature 2 meters above the ground, and the dew point temperature 2 meters above the ground, which is a way to get at the humidity from this data set. So calculating the actual wet bulb temperature isn't totally trivial because it requires an iterative algorithm, but luckily, again, the power of the open source ecosystem around X-ray and XAR is going to help us out here because there's this metpy, like it's a meteorology Python package, which has all sorts of functions for different types of meteorological and atmospheric and climate derived quantities, climate indicators. And it already provides an X-ray aware function for calculating wet bulb temperature for us. So if we just import that and run it on our subset of data, then this should not only will this calculate the wet bulb temperature, but it will also handle the physical units for us, which I think is awesome. So the output here is in degrees Fahrenheit, and it knows that even though we didn't explicitly say what these quantities were at any point. The reason that this is even possible is because I sneakily called pint.quantify here. And so what we're doing here is leveraging yet another open source library within the ecosystem, the Pint library and the Pint X-ray. And Pint is a Python library that basically promotes like systems of physical units to being an actual like type system in your Python code. And so what this means is that if you had like instead of having a NumPy array of numbers and a NumPy array of other numbers, you have like a NumPy array of n apples and a NumPy array of n like oranges. And with Pint, if you try to add them together, these Pint arrays, instead of adding together NumPy arrays, it will just like it'll let you execute with no complaints, even though it's like fundamentally wrong, the operation you've just done. It's nonsensical to add apples to oranges. But with Pint, it would raise an exception when you do that, and it would say units apples doesn't equal is different from units oranges. You can't add these together. So what Pint Quantify is doing is it's looking at all the metadata in this X-ray data set. For example, it's looking at how surface pressure is in the original data set. Surface pressure has pascals as an attribute, and then they get promoted to being an actual Pint array, and so it ends up displayed here neatly by X-ray, so that when that variable is passed in to metpy's function, metpy knows if it needs to do any unit conversions. And then on the final output, we're just casting it to Fahrenheit. And the fact that all of that is handled with no extra work for you is kind of amazing, in my opinion. And this is a really like underutilized part of the ecosystem. Um, so if you want to learn more about that, then you should read this blog post that I wrote all about it 3 years ago. So now that we've got this wet bulb temperature, let's try plotting it. So if we plot this for this time period, for this time point over India and Bangladesh, then we can see that the wet bulb temperature is like hovering in around 80 for like large parts of India and even higher for East India. And given that a wet bulb temperature of 95 Fahrenheit is often lethal if you don't have access to air conditioning, then this is clearly incredibly dangerously high. Um, and indeed, like our quick plotting like suggests the reality, like there were a lot of deaths from this event. Um, okay, so that was an example of a spatial analysis of a climate indicator. Um, for a sort of climate accelerated, climate change worsened event in the past. But let's try doing a temporal analysis instead. So
And
far
Tom,
we
before we do, you want
analyzed.
to answer a quick question? Sorry,
Yep.
before we do that, will you answer a quick question Durbin has about the temporal versus spatial groups?
Mm-hmm.
Just wanted to call that out. Sorry.
Let me find the
Q&A.
Q&A. Where is it in this interface?
I can just read the question. It says, sort of a random question, but what is the difference between the temporal and the spatial groups in the Arraylake? Is it related to data chunking schemes?
Yes, it is exactly, and I was about to explain that. And that's what this is about. So essentially, this you're exactly on the money. So like when ERA5 as distributed, ERA5 as distributed comes out with this like so-called pancake-like chunking, where each where the data is chunked along time but not along space, which means that loading the whole globe for one time point is efficient. But if you tried to load all time stamps for one location, you would be forced to load the entire data set into memory. And we don't want to be loading 40 terabytes onto our laptop, which is where I'm running this. Um, so the chunking is there. In that case, the chunking is suitable for spatial queries, but not for temporal queries. This is kind of like a fundamental restriction of the concept of chunking and the concept of file compression in the first place. And so one way that, but for this particular ERA5 subset, we wanted to be able to support both efficient spatial queries and efficient temporal queries. So the way we've done that is the quite simple but still effective method of just storing two copies of data with orthogonal chunking under different groups in the same store, where the spatially optimized chunking scheme is under the group spatial and the temporally optimized chunking scheme is under the group temporal. So these so-called like churro chunks. So hopefully that answers your question. We're now going to make use of that group. So if I open the other group, we get the same data and everything about this is the same, except that the chunk sizes, the chunking pattern is different. So you can see that it's got the spatial dimensions are now split up into small chunks. So we're going to use this temporally chunked version of the data to do a analysis of trends at a specific location. So as an example of like a climate indicator that you might want to calculate for a specific location, let's just try calculating the number of days each year that New York City experienced a heat wave. And so we're going to be effectively calculating a heat wave index. So first, let's look up what NYC's local authorities use to define a heat wave. And it turns out that they use the National Weather Service's heat index chart. And so they basically use this function of actual air temperature and humidity to define this heat index. And then depending on the threshold of the heat index, they have different sort of recommended so that's different implied medical risks and different recommended precautions, and above a certain threshold, it's defined as being a heat wave. So we want to calculate this quantity, and because this is a standardized quantity, then again, there's a metpy function for it. So we're going to select the variables. We're going to select specifically the latitude, longitude point over New York. So I've just chosen the numbers closest to New York here. Or actually, it snaps to the numbers, snaps the location closest to the location of New York here. I'm selecting just the variables that I'm going to need from the temporally chunked version of the data. Again, I'm going to load the data locally so that it's snappier to work with it. We don't need to re-download it. And I'm going to use pint to get the units. And so to do the actual calculation, then we need metpy has this heat index quantity. Okay, we've got the data. The reason that took a few seconds is because we loaded a considerable amount of data there onto the laptop over my home internet's network connection. And so the first thing we need, in order to calculate heat index, it takes relative humidity as one of the inputs, but we don't have relative humidity. So luckily, metpy has us covered here as well. There's a relative humidity from dew point function and then a heat index function as well. And so we can calculate both of these things. So now what we have is a time series of the heat index for every single hour over New York going back to 1975. You can see many, many time points in Fahrenheit because that's the unit of the heat index. And It goes all the way back in time to 1975. But New York City has it's the New York City's definition of a heat wave only cares about the maximum heat index reached on a given day. So let's sort of downsample this to calculate only the maximum value of the heat index in every 24-hour period. And X-ray makes this super easy because we can just coarsen the data by a factor of 24 because hourly data down to daily data and take the maximum of each of those windows. This is actually a special case of the general like group by pattern, which originally comes from like SQL, but X-ray implements a multidimensional version of, and coarsen is really just syntactic sugar around a particular case of group by. You can see that because we have the data locally, we can do this super quickly. And now we've got the maximum heat index on every single day going back till 1975. The reason why it oscillates like this is because the maximum heat index in winter is obviously going to be very low. But this looks sensible. It's got about the right magnitude. It gets pretty high in the summers, and it has an annual cycle. So the New York City's emergency management, they issue a heat advisory, which is the official name for a heat wave. If the heat index is greater than 95 Fahrenheit for 2 consecutive days, or greater than 100 Fahrenheit for 1 day. We're going to use this definition just for simplicity. And so we basically need to take our time series and find the number of days for which the temperature exceeded 95 Fahrenheit for 2 consecutive days. And again, there's another open source package which has a function for this as well. So XClim stands for X-ray climate indicators and has all sorts of various functions for climate indicators. So it has other things like heating degree days, which is pretty relevant for agricultural crop risk, for example. But we're going to use their heat wave index function. And you can pass the heat wave index function. We can say what's the threshold to be considered a heat wave, and the number of days in a row that have to have exceeded it in order for that day to have counted as having been part of a heat wave. And we can do both of these conditions in one call by calculating them separately and adding them together. And so once we've got this, then what this means, this is a plot per year. So this is the number of days in each of these years which would be considered to be a heat wave, a number of days for each of these years in which the New York authorities would have issued a heat advisory. And this looks plausibly right. Like the number of days is sort of in the low single digits most of the time. And as someone who lives in New York, that seems about right. If we look up the actual official predictions from the New York City Panel on Climate Change report, then we can see that we're in the right ballpark. And this is not bad, especially considering like there are a lot of caveats here. Like the original, this quantity would have been calculated from local weather station data, whereas we've calculated it from global reanalysis data. So we're not expecting the numbers to be exact, we're just expecting them to be close. The point is that it's remarkable that we can get even close with just like one Python notebook run in like 20 minutes. And it be so easy with these types of functions. So I think that's pretty awesome. And it really shows you that if you want to calculate climate risk for a locality that you're interested in, maybe because you live there or because your company has assets there or for some other reason, then this type of stack makes this very easy to do, even for multi-terabyte scale data sets. So just to summarize what we've done here, we've viewed and accessed various subsets of 40 terabytes of ERA5 data stored in the cloud and cataloged with Arraylake. We've plotted various quantities of interest, both globally and regionally at specific times, our spatial analysis, but we've also computed quantities of interest locally over the whole time history. And So to do this, we've used a number of open source packages, and then also the Earthmover platform and the Icechunk storage format in the cloud, and we've done it all from our laptop, which I think is pretty awesome. Um, so yeah, that's the end of my notebook. This is what I wanted to share with everyone. I thought this was pretty cool. I thought that in particular the ability to the combination of UV, Marimo, Pint, all working together to make this like actually really quite straightforward. So thanks for listening. Happy to take any questions that anyone has about this. I'm going to stop sharing now. I see one question. Thanks for the interesting presentation. Just curious if the ERA5 data for New York is corrected for the local time zone. All ERA5 data should be in UTC. Maybe I missed it. You may have just spotted a bug in my notebook because I didn't really think about that. But there are various ways to handle that kind of thing in Python fairly straightforwardly because there's these nice libraries like CF time and so on. Um, I don't think for our heat index calculation it would end up mattering because we took the maximum over every day anyway. But yeah, good question. Um, cool. I think that's all the questions that I can see. Um, do you know if there are any other questions, Cheryl?
Nope, that's it.
Great.
Anybody wants to ask live, I can open the voice. Feel free to just raise your hand. Click the raise hand. I think that's it.
Okay, great. Well, in that case, oh, I see something. Kevin. Hi, Kevin. How you doing? Great presentation. I'd love to share this with my students. Can anyone freely access? So the yes, they can freely access this. They do need Earthmover accounts, but they can make an Earthmover account for free just by clicking on the link, in the same way that you can with GitHub, for example. This is a public repo in the Arraylake platform.
And I'll be
Yeah.
sending an email later today with a recording of this webinar along with the link for easy access. So what other data sets are publicly available on Earthmover, Tom?
Oh, yes. Good question, Malcolm. If you make an account, you can browse through various data sets that we have. At the moment, we mostly use it to host demos, but we are just we are now planning to make some important data sets available to customers, particularly um, weather forecast data sets like IFS. So in a month, so at the moment, the answer is mostly like demo subsets of things like ERA5. But in a few months, then the answer might well be like large copies of all sorts of important weather forecast data sets. But you can also you can look today and have a look around yourself in all the public repos and the Earthmover public organization on Arraylake. Okay. I don't see any more questions. Thanks for coming, everyone. I hope you enjoyed that.